In this lecture we're going to look at estimation, and in particular confidence intervals. As in the beginning videos, lectures of this material on estimation, told you that when we got to confidence intervals we would turn the thing around. We would start with sample information and say something with that sample information about the population. Up to this point we've always had population information. It said something about a sample and talked about probabilities, which were perhaps not so exciting, but now we get into interval estimation, confidence intervals, and we start with sample information as we do in the real world and say something about the population. Right? This exact same mechanism that we will do in this lecture is done in the media when they talk about opinion polls and say that 55% of the electorate liked candidate so and so, and in the guts of the paper, if you're lucky, you'll see that this number, the 55%, is good within, say, plus or minus 2 percentage points, right? And that essentially is a confidence interval. They don't get into any detail, but that's a confidence interval. Right? We're measuring something like an average or a proportion with an interval, and that the width of the interval will give us the level of confidence that we have in our estimation. If it's very narrow, it's great. If it's wide, it's not so great. Alright, the whole concept of estimation starts with the sort of the central limit theorem, and the fact that if we talk about averages, one sample, that this normal distribution represents the probability distribution of all possible sample averages for a given sample size n. And as before, we could talk about probabilities of finding sample averages within that span. Okay, let's for right now assume that we have calculated limits on this distribution, symmetrical limits, such that we get 95% of the distribution within those two limits. That means, since it's symmetrical, we'll have 47.5% here and 47.5% here, and in each of the two tails we'll have 2.5%. Alright, we don't need to worry about how that calculation is done. We can do it, and it's not that hard. Alright, but this is for the true distribution. The true distribution is only known if we know mu and in fact sigma. We can get away or get out of knowing sigma, but we can't get out of knowing mu, the population mean. Alright, so let's hope I can draw these to scale. Let's say that we don't know where this distribution is, but I get a sample value, take a sample of that particular given sample size, say 100, and let's say my sample winds up here. Let's draw a new number line for it. Alright, and let's duplicate this distribution, or the width of this distribution, on this new number line. Okay, I'm trying to do it sort of faithfully. Alright, and here's the width here. Okay, so this is supposed to be this same interval, just moved sideways. Okay. Well, what happens? Well, the true mean, which we have no idea where it is, falls within the interval. Haha, that's great, right? Okay. What happens though if we get a sample average outside the 95% interval? Okay. And let me try to duplicate this distribution again. not sure I've drawn it exactly to scale. But now when I have my sample value outside, which is sort of unlikely, but it happens once in a while, alright, say 5% of the time it'll lie outside of this 95% interval. But now the true average doesn't lie within the interval that I've just calculated around this particular sample average, alright? And that's the crux of the matter. Most of the time, 95% of the time, we will find a sample average within here and here, right? Within these two intervals. When we do so, the interval that we will reproduce or try to reproduce around such sample averages, for instance here, will contain the true average. For those averages that lie outside here, we will construct intervals that are outside, okay, that do not contain the population average. Okay, so these are confidence intervals. So we would say that 95% of 95% confidence intervals, which I'll abbreviate CI. Right, those are the ones that we calculate around sample averages within the 95% interval on the top, on the real distribution. 95% of these will have 95% confidence intervals that contain mu, and that's great. Okay, it's something that we can use. But realize that obviously 5%, the others, of these 95% confidence intervals do not contain. Oops. So 5% of these 95% confidence intervals will be wrong. Okay. Calculation of these intervals is not hard. What we have to do is we start with a middle of the distribution, and we'll go up and down, plus and minus some distance. Alright, that distance will be z with, if we're going to have 2.5% in each tail, we'll have z with a subscript 2.5% times what we would like to have is sigma sub x bar. The only trouble is we don't have sigma, we don't have the population standard deviation. Alright, so we'll have to estimate that with S sub x bar. And that'll imitate the 95% interval on the true distribution. By the way, S sub x bar will be calculated just like sigma sub x bar. Alright, from the previous lectures. Alright, just different notation. So this is the estimated standard deviation, and this is the true value, the real value. And then the other notation, right, x bar, you know, the sample average. The other notation, the z with a subscript. So if I tell you z 0.025, that means that on the diagram, the z distribution, I've got 2.5% in the upper tail. Alright, so this is z with a subscript 0.25. How do we find that? Well, actually we do it, remember that there will be 47.5% between 0 and that limit, so that in total 47.5 plus 2.5 is 50%. So we go to our tables, look for 0.475 in a manner just like we did for percentiles, and find the z value. The 2.5%, oops, is a famous value. It's on the 1.9 row, the 0.06 column. Right, let's find that. So it's on the 1.9, 0, 1, 2, 3, 4, 5, 6. Okay, so that's that value there. Right, so it's 47.5% between 0 and 1.96. So Z with 2.5% is 1.96. Let's do another one just to make sure that we can handle it. Another common one will be 1% in the tails. Alright, so it'll leave us with 0.5% in each tail. 0.5% as a decimal is 0.005. So if we have 0.005 here, we'll have 0.995 between 0, sorry, not 995 of course, 495 between 0 and that limit, Z with 0.005 in the tail. So let's look for 495. Alright, and you'll see it's, oops, wrong value here. It's between these two numbers, right? It's halfway between them. So this is a 2.5 and either 2.57 or 2.58. Okay, so we will call it 2.57 or 2.58, and to be safe we'll just use 2.58, the larger number.